All right. Uh, Good afternoon, class. Mr. Pettibone here. Um, I want to remind you that I posted the last quiz um, last last night, and this quiz is due on Thursday. So Thursday at 11:59 p.m. My plan is to grade everything on Friday and just have uh, the grades finalized before the weekend. So make sure that you turn that in. I think it's a good quiz. The reason I posted it so late is because I really tried to make the numbers like actually realistic. So I was doing a lot of research, figuring out like how many stars are in a small galaxy, and you know I did a lot of research to make the numbers as accurate as possible. So the frequency of the photons, for example, is the actual frequency that a hydrogen atom emits. It's called the Lyman alpha photon. Is the quiz the last grade of the year? Yes. Um, there have been a lot of students who have been frantically emailing me about stuff, and it's like they missed the overall message that I said to them on the day that the school closed, which was that I'm not going to penalize you for the pandemic. Okay? So your grade is not going to go below, even if your grade says you have a 70%, if you had a 95% when the school closed, then when you get your final grade, it's going to read 95%. Okay? So I've been getting hassled by a lot of people who had an A when the school closed, which means that they're going to get an A, but then they've slacked off during the pandemic and haven't submitted homework, so their grade went down. Even if your grade says that it's lower than it was when the school closed, I will override that and give you the grade you had when the school closed. Okay? So, um, so many of you have an A, but you're acting like you're gonna fail. Okay, you're not gonna fail. You have an A. There's an assignment in the grade book. It's called your grade percentage on 313. That is the lowest possible percentage that I will give you in the class. Okay. Um, so let's get to today's lesson. This lesson isn't on the last quiz. This is just kind of for fun. I wanted to talk to you a little bit about special relativity. And special relativity is it's a theory that was developed by Einstein in the beginning of the 20th century, so early 1900s. And basically, special relativity came about because of a certain fact, okay, which is that everyone measures the same speed of light. Okay, so light is really weird. Okay, so what I want you to imagine this, and Einstein was famous for these. He had what were called Gedonken experiments, which means thought experiment. So Einstein really liked to do Gedonken experiments, and so imagine this. Imagine that a train is traveling eastward at 20 miles per hour. What if you sprinted down the aisle of the train in the eastward direction at 10 miles per hour? Okay? So the train is going at 20 miles per hour. You are running down the train at 10 miles per hour. How fast would someone observe you to be traveling if they were watching the train? Well, hopefully you know that the correct answer would be 30 miles per hour, okay? So your velocity, because you're running in the direction of the train's motion, your velocity adds to the velocity of the train, and so as a result, those two velocities would add. If you ran westward at 10 miles per hour, and the train is going eastward at 20, then people on the ground would see you as traveling at only 10 miles per hour to the east, okay? So basically velocities are going to add or subtract. But it turns out that this is only true if something is not going close to the speed of light, okay? So if something is going close to the speed of light, then we have to sort of modify the rules, okay? And in particular, everyone measures the same speed of light. So for example, and also nothing can go faster than the speed of light. Okay, so let's apply that train logic to a beam of light. What if a train is going eastward at 20 miles per hour and someone on the train shines a flashlight in the eastward direction? Does the beam of light look like it's traveling at 20 miles per hour plus the speed of light, according to an observer of the train? You might think yes, but then because that would be the same logic for if you were to run down the aisle of the train. But if something is going at the speed of light, everyone measures it going at the speed of light. So it can't be going 20 miles per hour plus the speed of light, because that would be faster than the speed of light. Okay? So the person on the train would measure the beam of light as traveling at 3 times 10 to the 8th meters per second. And the person outside the train who's watching the train would also see the light traveling at 3 times 10 to the 8th meters per second. So it takes some, it's sort of difficult for that to sink in for people. Light is different. Everyone measures light to be traveling at the same speed, which is 3 times 10 to the 8th meters per second. And nothing can go faster than that, all right? The theory of special relativity, it just doesn't work if things go faster than the speed of light. So sometimes people ask, well, can you go backwards in time if you go faster than the speed of light? And the answer is it doesn't matter, because nothing can go faster than the speed of light, as far as we know. Okay? So this is what the theory of special relativity addresses. And then a couple of years later, Einstein came out with the general theory of relativity, which pertains to situations where something is going close to the speed of light and gravity is significant. So the general theory of relativity has to do with gravity. The special theory of relativity has to do with things going close to the speed of light. Okay? Hello to all the people watching, Akshay, Christian, Jackson, and Charlie. So the important thing to calculate in special relativity to figure out how important is relativity is something called gamma. And gamma is equal to 1 over the square root of 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light. Okay? So in particular, what is gamma going to be equal to if your velocity is 0? If your speed is 0, it would be 1 over the square root of 1 minus 0 squared, which you can figure out is equal to 1. Okay? What is the relativistic gamma if your velocity was equal to the speed of light? In that case, it would be 1 over the square root of 1 minus c squared over c squared, which would be equal to 1 over the square root of 1 minus 1, which would be 1 over 0, which is infinity. Okay? So basically, the relativistic gamma is 1 if you're going slow compared to the speed of light, and it becomes infinite the closer you get to the speed of light. Okay? If you were to graph the relativistic gamma versus speed, it starts out at a value of 1, okay? And the value stays pretty close to 1 for a long time. But then it has a vertical asymptote. It goes like this. And it has a vertical asymptote as the speed approaches the speed of light, okay? So the graph kind of looks like this. Wow, so it looks like that. All right, so if gamma is much greater than 1, gamma being much greater than 1, signals that special relativity is very important. Okay? So basically that means that we're going to have to go against our intuition for how we think about the world. Because in our everyday experience, we travel much less than the speed of light. Okay? So for our everyday motions, gamma is basically 1. All right? So that means we've developed our intuition for a world where everything has gamma approximately 1. But if we had grown up in a universe where things were going closer to the speed of light and we had interaction with those objects, we would have a much different sense of the way the world works. Okay? So in particular, the thing that I want to teach you about today is something called time dilation. Okay? Okay? So in particular, so what time dilation, and I'm not going to derive it. If you would like to see the derivation, actually you could watch my CHL lectures from the past 2 weeks where I've actually derived the formula for time dilation. But since this is a first year physics class, I'm just going to give you the formula. Excuse me. So time dilation is the fact that moving clocks run slower than stationary clocks. Okay? And so we've actually tested this. We've tested this in numerous ways. One of the ways that we tested it is we put accurate clocks, we put atomic clocks in airplanes. Okay? So what we did is we took two atomic clocks. We synchronized them, and we took one of the atomic clocks and we put it on a 747, and we let it fly around on the 747. I think that they just put it on an airplane with passengers, right? It was just part of the cargo, all right? So they put it on that airplane. They just let the atomic clock fly around all year long, and then afterwards they let it land, and they compared it with the other atomic clock, which had been on Earth the entire time, not flying around. And the atomic clock that had been flying around was actually less time had elapsed for the atomic clock that had been flying around. Okay. Another way we've tested it is with satellites. Did you know that we manufacture satellites? Satellites are manufactured on Earth, right? And we manufacture the clocks on satellites to run too fast. Okay? They're running slightly too fast. Then, once the satellite gets put into orbit, now it's in orbit and it's traveling very fast around the Earth. Because it's traveling fast, its clock is now running slower. But because we synchronized the clock so that it was running too fast on Earth, once it goes into orbit, it actually runs in perfect synchronization with Earth's clocks. So that's kind of cool. So this is an actual feature of satellite design. If you need to, GPS satellites need to have very accurate timing. And so we have to account for special relativity in GPS satellites. Another place where we have evidence of time dilation is with unstable elementary particles. In particular, I'm going to look up, say, for example, a muon. Muons are unstable. Let me look up the lifetime of a muon. Give me a second here. I'm looking up the lifetime of a muon. Remember, a muon is like a heavy electron. A muon has a lifetime of 2.2 times 10 to the minus 6 seconds, 2.2 microseconds. And so what happens with a muon, okay, is it's unstable. So if you have a muon, I'll draw the Feynman diagram here. The muon will decay via the weak force. So you have a muon, it decays into a muon neutrino, and then this would be a W minus, and then the W minus decays into an electron and an anti-electron neutrino. Okay, so basically what will happen is if you had a muon, it will turn into an electron plus an anti-electron neutrino plus a muon neutrino. Okay, so the muon is unstable, and this process happens in 2.2 times 10 to the minus 6 seconds. Okay, this is if the muon is at rest. But if the muon is moving, it's going to live longer because its clock will run slow. So this 2.2 times 10 to the minus 6 seconds is going to be extended if it's moving. So there's a formula. It's called the time dilation formula, and it basically says the time elapsed if you are at rest, okay, divided by gamma is going to be the time that elapses if you are moving. So see how if you are at rest, okay, so this is the time that elapses for the moving thing. Okay, and this is the time elapsed for someone watching the moving thing. Okay, and then this is the relativistic gamma. So it depends on how fast the object is moving. Okay. So let's suppose, Akshay, I see your question, and I think this example is going to clarify it. Okay. So let's suppose a muon is emitted at 0.96 C. So when I say 0.96 C, that means 96% the speed of light. Okay, so this muon is going very fast. How long will it live for? According to observers. Okay, how long will it live for according to observers? So first thing we have to do is we have to figure out what is the relativistic gamma. So notice how V over C is 0.96, 96% the speed of light. So that means that V squared over C squared is 0.96 squared. Okay, 0.96 squared is 0.92. Okay, so gamma is going to be 1 over the square root of 1 minus V squared over C squared, which is 1 over square root of 1 minus 0.92, which is 1 over the square root of 0.08. And that gives us 3.57 is gamma, okay? So if we look at our formula, the time at rest over gamma equals the time if it's moving. So the time that elapses before the muon dies, according to the muon, is 2.2 times 10 to the minus 6 seconds. The time that elapses for us, we're trying to calculate, and gamma is 3.57. So basically, we just have to multiply across the 3.57, and we get that the time that we observe the muon to live for is 2.2 times 10 to the minus 6 times 3.57. So it's going to live 3.5 times as long, 7.9 times 10 to the minus 6 seconds. Okay, so it's going to live longer because it was traveling fast. So it's time was going more slowly for the traveling muon. So we see this all the time. And it'll live longer the closer it goes to the speed of light. I had another thing I wanted to talk about. Oh yeah, there is something called the twin paradox. Okay, so what if you have two twins? They're both born at the exact same time. Actually, twins are never born at the same time, but let's say that they both entered the world at the same time. It was a fluke of nature where they both came out simultaneously, okay? It wasn't one then the other. So they have the exact same age, okay? And one of the babies goes in a spaceship, and that spaceship flies around at close to the speed of light, okay? Now, because the baby is flying around at the speed of light, close to the speed of light, time is going to go extremely slow for that baby, okay? And, okay, so this baby's flying around. Let's say on Earth, the other twin, 50 years elapses. So the other twin grows up to be 50 years old. And all the while, this spaceship is going at close to the speed of light. So this one is going to be, and then this spaceship lands on Earth. Then because the spaceship was going so close to the speed of light, that baby might not have aged hardly at all, depending on how close to the speed of light it was. So while they were the same age at birth, because one of them spent time going close to the speed of light, when they come back together, one twin will be 50 years old, the other one will be still a baby. Pretty bizarre, but it's for real. So that's called the twin paradox. You can look it up. There's a great book. I don't know if you guys have read it before. It's called Ender's Game. I'll type it in there. It's one of my favorite books when I was your age. Still is one of my favorite books. But in that book, there is a war between humans and aliens, okay? And there's a general who figures out how to defeat the aliens, okay? But the thing is that they didn't completely annihilate the aliens, so they know that there's another war coming in the future, okay? So after the war ends, they're like, we need to save this military genius because we don't know when the next war is going to be. So they take the military genius and they put him in a spaceship and they have him fly around at close to the speed of light. Okay? And so time is going by really slowly for him, so he's not aging. Okay? And so they just keep him flying around in outer space at close to the speed of light. And then when the next war comes, they bring him out of light speed, and they bring him back, and he can help in the second war. All right. So I think that's pretty cool. Another interesting idea is I think our economy would collapse if we were to go close to the speed of light, right? Because what would happen is if we could go close to the speed of light, I would invest some money in the stock market, and then I would head off in my spaceship at close to the speed of light. Time would go by very slowly for me, all the while my money is accruing exponential growth in the stock market. And so maybe 1 year passes for me on my spaceship, but then back on Earth 200 years passed, and my money has been having exponential growth for 200 years. So I would come back and be a very, very rich person. And so the reason I say that if light speed travel becomes a reality, then we're going to have to completely rethink our economy, because what would happen is everyone would just spend time at light speed. And so no one would be left on Earth, right? We would all just put money in the stock market and head off at light speed. We're going to do some more examples of this tomorrow, and I'll also teach you about something called time dilation. So I hope you enjoyed the lesson. I hope you